Right. It's a pleasure to be here this morning to share the work that's been done over the last 2 decades at the center of the galaxy. And this is an area of research that's been advanced tremendously through the progress that's been made in the ability to make high-resolution imaging. So there's a progress both on the front of technology and science. The technology was driven initially by the question of, is there a supermassive black hole at the center of our galaxy? And now we can answer that question with a resounding yes. And we've turned the center of our galaxy now into a wonderful laboratory for understanding both the physics of black holes, understanding new tests of general relativity, as well as new tests of the astrophysics of black holes, understanding the role that black holes play in the formation and evolution of galaxies. All right. So let me just turn to those 2 big picture questions again. So from a physics perspective, black holes are really interesting to study because we want to know whether or not these supermassive black holes exist. And in this talk, I'm going to distinguish between the ordinary mass black holes and the supermassive black holes. So the first was predicted by theories of how massive stars formed, and we predicted the existence of ordinary mass black holes, which are roughly 10 times the mass of the sun. And of course, gravitational wave experiments today have given us wonderful evidence that these roughly 10 solar mass objects exist. The supermassive black holes are 1 million to 1 billion times the mass of the sun, and they were not predicted by theory, but rather driven by observations that suggested that they existed at the center of galaxies. So these experiments are driven by our desire to prove that these 1 million to 1 billion times the mass of the sun objects really do exist, and then to turn these into laboratories for understanding how gravity works. From the astrophysical perspective, in the beginning, actually 2 decades ago, it used to be posed as a chicken or an egg question. Which came first? Was it the supermassive black hole that seeded the galaxy, or did the galaxy form first and then form the black hole? But today we understand that that wasn't even the right framework to pose, but rather it appears that whatever mechanism formed the black hole synergistically formed the galaxy. And we see that because we see a correlation between the mass of these supermassive black holes and the mass of the central part of these galaxies, known as the bulge. So we want to understand what roles the supermassive black holes play in regulating the growth of these galaxies. And our galaxy provides us an amazing laboratory for understanding or seeing processes that simply can't be seen in any other galaxy, because our galaxy is the closest center of a galaxy we'll ever have to study. The next closest galaxy is 100 times further away. All right, this work that's been done by several groups has been advanced by many frontiers in technology. There are 3 in particular that are important. First is the advancement of detectors that are sensitive to infrared radiation. The center of our galaxy is absolutely invisible at for optical light. 1 out of every 10 billion photons makes it to us in the optical. But if we look to the infrared, 1 out of every 10 photons makes it to us. So our center of our galaxy becomes visible. So it's absolutely critical to have infrared detectors, and the advancement in infrared technology has been tremendous over the last 40 years. The second piece of this is the need to get to a very, very high angular resolution. This work has been driven by the ability to measure stellar orbits. And the direct proof of a black hole is to show that there's a lot of mass inside a very small volume. So you want to see the stars that are as close to the center of the galaxy as possible. So you want the highest resolution as possible. So diffraction-limited is given by lambda, the observing wavelength over the diameter of the telescope. So you are driven to very large mirrors. So there's been tremendous progress in the ability to build large telescopes through segmented technology, and not only single telescope, but now, most recently, the ability to combine the light from multiple telescopes at infrared wavelengths. All of this is dependent on our ability to overcome the blurring effects of the Earth's atmosphere. So the Earth's atmosphere introduces lots of aberrations, so you lose about a factor of 20 in angular resolution compared to a single large telescope. So this technology, which has made, again, lots of progress over the last 20 years, has been critical. And in fact, there was a key piece or a key moment when technology was declassified by the military, and I'll get back to that in a second. Okay, so this work has been, in terms of measuring the stellar orbits, has been really pursued by two groups. It requires a long time baseline in data. This is two decades of data sets. So the first was started on the NTT by the MPE group. And it's progressed through a sequence of larger telescopes and the ability then to combine telescopes with gravity. And then the other group was led by me using the Keck telescopes starting in 1995. Both groups use very similar techniques in the beginning. So in the beginning, both groups used a technique that is hardware simple and software complicated. So it's basically treating the atmosphere as an opportunity to think of the telescope as a little mini interferometer. So you're basically looking at interference patterns and analyzing them in a Fourier deconvolution sense. So on the left is a very early animation of real data. This is not image process. This is the real data that you get when you just shift and add all the short exposures. There's an image that's about 10 times bigger than both the images on the left and right behind it. So I'm just zooming into the central piece to give you an appreciation of the kind of data that the teams were able to achieve. It's really wonderful to see these animations because I have to share with you when these experiments were first proposed, the common viewpoint was that they wouldn't work because the telescopes were segmented so that you couldn't get to the diffraction limit. And even if you were, you wouldn't see stars, and even if you could, you wouldn't see them move. So it's really wonderful just to see an animation because you don't need a computer to see these stars moving. You can probably identify what's for most of us is our favorite star. Its name is SO2 or S2. We were hearing about S2 a moment ago. This is a very different S2. This is the name of a star. So on the right, you see that star more clearly. And this is what you can get with an adaptive optics system. So adaptive optics is the hardware complicated, and you would hope software simple, but of course that you never get that. It's always software complicated. But nonetheless, this is the technology that was advanced by the military to use hardware solutions to remove the distortions of the Earth's atmosphere by a deformable mirror where you can move little segments on kilohertz timescales. Okay. Today, you can combine the light of the 8-meter telescopes at the VLT. And with that technology, you get a field of view that's the size of an individual star, but has a resolution that's 10 times better. So this again, has advanced us further. All these advancements, and in particular with adaptive optics, allow us now not only to take images, but to also take spectra. And of course, spectroscopy is incredibly important because it allows us to do two things. One is the images allow us to measure the dynamics in 2 dimensions on the plane of the sky, but of course you're missing the line of sight motion. So with spectroscopy, you can measure the Doppler shift and more, and that gives you the motion along your line of sight. So that gives you now 3-dimensional motion at the center of the galaxy. And then for the first time, and this is only in the last 10 years, you can actually ask what is the astrophysical nature of these objects that you've been treating as point particles for the first decade. And I have to say, this has been one of the most remarkable aspects of the work that's been done here is that so many surprises have been revealed by the ability to take spectra. Okay, Now let's first start off looking only at our knowledge of the central potential. So SO2 dominates our knowledge of the central potential, and now I'm zooming in even further. So in the beginning, I was just looking at the central arc second. And for those of you who don't think in arc seconds, degrees, there's 60 arc minutes in a degree and 60 arc seconds in a arc minute. And this is a quarter of an arc second by a quarter of an arc second. For most astronomers and astrophysicists, this is a ridiculously small field of view. But nonetheless, it allows us to see stellar orbits. And this animation has become more and more complicated in order to depict a couple pieces of information. So stars are tracked in imaging space alone when they're trailed by a dashed line. The minute that star can be seen spectroscopically, it's trailed by a solid line. So you can see the progress in technology. So stars appear not because they're variable star, but rather because you can see deeper. The adaptive optics images allow the teams to see about a factor of 10 times deeper. Okay, so SO2 now gives us the strongest evidence for a supermassive black hole at the center of our galaxy. And over the course of the 20 years, the inferred dark matter density has increased by a factor of 10 million. I mean, this is an enormous step forward in terms of the evidence for the existence of the supermassive black hole. And this is a plot that shows the inferred dark matter density as a function of inferred black hole mass. When you're under the green line, that case are cases which can be explained by other objects. In other words, they could be clusters of dark objects. They could be these fermion balls that were suggested as alternatives. But the red line shows the progress for the center of the galaxy. In the beginning, all we could measure, the teams could measure is velocities on the plane of the sky. Then it became possible to measure accelerations, and then full orbits. So now you're up at a density of 10 to the 15th solar masses per cubic parsec. So anyway, this gives us an incredibly strong case, and for many, many years, the strongest case for the existence of supermassive black holes. It was actually the strongest case until last week. All right. Looking forward, we're no longer interested in advancing the case for supermassive black holes, but rather using this as a laboratory for understanding the physics of black holes. So SO2 now offers us a direct test of general relativity near a supermassive black hole. Now, this is only possible once you know for certain the characteristics of the orbit. In other words, to get a seat at the table to make these measurements, you have to have measurements of the star going all the way around. And as you can already see, well, I can tell you, the orbital period of the star that's strongest at this is 16 years. And then the next time it goes through closest approach, you're in the business of being able to do these relativistic tests. Okay. Now, these days we're talking about a lot of tests of general relativity, both in our galaxy and elsewhere. So it's really important to be more specific about what aspects of general relativity are we looking at. And with the orbits of stars at the center of the galaxy, there's actually 3 different tests, and I've ordered them in order of difficulty, or you can also think of this as a sequence in time that these will be possible. The first one has just been achieved, which is the detection of gravitational redshift. Okay, so this is looking at the impact of the curvature of space-time on the photons travel from the object to us. The next test is the precession of the Periapse, which is actually looking at how the object moves through space-time itself. And then lastly, there's the goal of measuring the spin of the black hole, which of course would be a phenomenal achievement because black holes are incredibly simple objects. There's only 3 characteristics of black holes. They have a mass, they have a spin, and a charge. We've got the mass, and in this case, we'd like to measure the spin. In the course of doing these ultra-precise measurements of stellar orbits, one also gets to explore other astrophysically interesting questions, which is the question or the possibility of having dark mass at the center of the galaxy, either in the form of stellar remnants, black holes, neutron stars, as well as dark matter. So that's the future. So let's look at where we are today. So SO2 is the first to go through Periapse, closest approach with the full orbital phase coverage. And on the left, I'm showing you the images. So again, now we're starting to look at real data as opposed to animation. You can see just the progress. You have a clear orbit. And on the right is the radial velocities, the velocities along the line of sight that you get from spectroscopy. And you can see the tremendous changes that occur. So in fact, at closest approach, one has to also disentangle the Keplerian component from the relativistic component. Closest approach was also tracked by this wonderful new experiment of gravity, which combines the light of the the 4 8-meter VLT telescopes, which gives a wonderfully precise measurement of the position of SO2 with respect to the black hole as it goes through closest approach. Now, as it went through closest approach, this is an event that has been anticipated by many groups for a decade. It was 10 years ago, roughly, that people started to understand that the orbits of the stars at the center of the galaxy were short enough, and the measurements were becoming precise enough. In other words, once we got to the regime of adaptive optics, was it clear that one could get beyond just asking the question of the existence of the black hole? Everybody was very relieved to understand that this closest approach would actually happen when the center of the galaxy was observable from Earth. I mean, this is astrophysical work like this is seasonal. The Earth goes around the sun, so there's actually half a year in which you can't see the center of the galaxy at these wavelengths. So the shaded region shows the visibility of the center of the galaxy. And in fact, while we think of this, well, in physical space, there is one moment in time that's critical, which is the moment of closest approach. But we don't have the privilege of measuring that three-dimensional position. We're actually measuring 2 dimensions of position and 1 dimension in the third dimension of velocity. So in fact, there are 3 events that were critical to capture at closest approach, because it's what I call the turning points, or the maximum and minimum, that are critical for constraining the properties of an orbit. So within this 6-month window, there were actually all 3 events, which is the closest approach of the black hole in image space, which is tracked by the green line. That happened in May. And then the radial velocity along the line of sight went through this crazy maximum to minimum change. So it changed from about 4,000 kilometers per second to minus 2,000 kilometers per second in the space of just a month or so. It was a really radical change. So in fact, one of the interesting things to develop, that was important to develop, was understanding in these experiments which measurements were the most critical to make. You actually have to make 3 kinds of measurements. You have to make the spectroscopy measurements, the basic imaging measurements, and a third, which I have to say 20 years ago I probably would have told you I thought was the most boring topic, but it's the one I think about the most these days, which is something known as the reference frame. You have these precision measurements, but you have to get into a common reference frame. We can do this spectroscopically pretty easily, but imaging-wise it's really difficult in a field where everything moves, and not only is everything moving, but everything is accelerating at some level around the supermassive black hole. So a precision reference frame is tricky business. Okay. At closest approach, you get this relativistic redshift, which contributes an extra 200 kilometers per second on top of this 6,000 kilometers per second change. And what's shown in the animation is an exaggerated view of the precession of the periapse. So that's not measured yet, but that is the next goal. The measurements of the gravitational redshift have come in, and one sees it beautifully. So this is the deviation from the Newtonian orbit. So if there were no relativistic effect, it would be a flat line. And what we're seeing is this, the predicted 200 kilometers per second. Now, I have to warn you, you have to be very careful about interpreting this plot. So it's easy to put a PR plot and say, ta-da, this was easy. But actually, one has to know that this is a differential measurement, and that, in fact, the dominant source of uncertainty is your knowledge of the Newtonian orbit behind this. Okay, so all of this actually gets much, much better as your knowledge of the orbit improves. In other words, this is still early days. And And it's early days in a model that has 17 parameters that one has to solve for, and there are a lot of degeneracies. So in the various reports of the gravitational redshift, it's really important to remember that the uncertainties depend on the number of variables you've allowed to be free or put strong constraints on. Because today, systematics absolutely dominate the uncertainties. So you can get a very precise, from your statistical uncertainties, but in fact, it's a game of systematic errors, as are most precision measurements. Okay. Again, I could put up a plot that shows the agreement between the two reports, but it's actually more interesting to put up the disagreement. So it's easy to mask it when you project in a 17-parameter model when you marginalize over all the other parameters to just look at the gravitational redshift. But the gravitational redshift depends on your assumptions about the mass of the black hole and the distance to the black hole, in particular your distance. And you can see here that at a more than 3 sigma level, these two experiments that have recently been reported actually disagree. So, and the reason I emphasize this is these kinds of disagreements are critical to get on top of if you want to make your next step to the precession of the Periapse. The precession of the Periapse is a much harder experiment. You really have to have complete control of your systematic errors, and in particular, your astrometric reference frame. Okay. There are all sorts of other fun things that have been thought about in terms of understanding what might have an impact, like the possibility of a hidden companion. So experiments have been able to put limits on this kind of companions. And in fact, this experiment also allows you to consider the possibility of a fifth force. So this shows simply that the orbits at the center of the galaxy offer a new angle on thinking about the constraints on the fifth force. And again, these experiments just get better with time, as well as the technology that is advancing to improve the precision of the measurements. So as I alluded to, there are many upcoming promises, both in terms of our ability to measure the prograde precession of Periapse. So in other words, the orbit will not come to the same point, it will overshoot. And of course, extended mass does the exact opposite. It's a retrograde precession. So many teams are targeting the ability to make these kinds of measurements coming up, but it's really important to note there's a degeneracy between these two physical effects and then the reference frame. So one needs at least 3 stars to play with. And fortunately, there are multiple stars at the center of the galaxy that you can play these games with. So let me now turn my attention to the astrophysical piece. In other words, the environment around the black hole. And the center of the galaxy has absolutely taught us to expect the unexpected. And in this animation, one sees a color coding for the kinds of stars that are being tracked. The aqua type star coloration are young stars. And this was surprise number 1. Young stars are not expected to be near a supermassive black hole. Supermassive black holes have incredibly strong tidal forces, and the gas densities in this region are incredibly low. So this leads one to assume that there's not enough self-gravity in order to form stars. And this is not a little inconsistency. This is multiple orders of magnitude. Something like 10 to the 11th, a factor of 10 to the 11th in terms of what the densities that you see and what you need to actually have star formation proceeding today. And yet, what you can see from these animations is that that's the dominant population of stars. So there's a mystery to solve associated with how do you form stars in this incredibly inhospitable environment. And the orbits give us an important clue. So if you look at this animation, as it pulls back, you start to see the presence of a stellar disk. And that leads us to believe that the leading hypothesis today is that roughly 1 million years ago, there was an accretion disk around the central black hole that had gas densities that were much higher than we see today that led to the formation of these objects. And in fact, much of the thinking can be borrowed from the formation of planets because the mass ratio between the stars in the black hole is identical to the ratio of planets to the host stars. So a lot of the dynamical work, there's a nice crossover between the centers of galaxies and exoplanets. Okay, so that's unexpected result number one. Unexpected result number two is that old stars, which are roughly 1 billion years old, billion years at the center of the galaxy, have had plenty of time to dynamically interact with their environment. And the anticipation is that they should congregate around the most massive object in the system, or in the center of the system. So one predicts that you should see an excess of old stars at the center of the galaxy. Now, the old stars are color-coded orange. And you might notice a dearth of the old stars. So this has led to a whole other avenue of research for both the theorists and the experimentalists to understand, well, why don't you see these old stars? Where have they gone? Now, unexpected result number three is what I'm going to give a little bit more time to, because it's actually the most recent unexpected result and has really nice potential connections to the gravitational wave detections. So these are the magenta objects in here. These were the objects that nobody thought to make predictions for. Okay, so these are the first spatially resolved tidal interactions that have been seen around a supermassive black hole. So that's an important process that people invoke all the time for the growth of black holes. The idea that as objects come really close to the black hole, be it a gas cloud, be it a star, they have the potential to tidally disrupt. That'll change the nature potentially of the object and provide an important feeding source for the black hole. So what nobody debates is that this tidal interaction has been seen. So you see the tidal tails, you see them grow as they approach the black hole, and then they go through the closest approach, and in this case they survive, and then they shrink again. Okay, so there's been lots of ideas about what this kind of object is, but I want to give highlight, and again I'm a little biased here and I'll fess it right up front, is the idea that there might be, these might be produced by three-body interactions that arise from thinking about a close binary star near a supermassive black hole, where the black hole is driving the binary star to merge through what's known as the Kozai-Leadoff effect. So it's basically a three-body interaction. What's interesting is that once you start to consider that there's the density of stars increases as you go to the center of the galaxy, this provides a potential connection with these gravitational wave sources as a way of creating objects or stellar mass black holes that are much larger, more massive than were predicted. Now, for a long time, people wondered whether or not binary stars could exist at the center of the galaxy. In other words, whether or not this was an environment that could sustain two objects being bound for a long period of time. But in fact, observationally, we do see evidence of binary stars. And these binary stars are being discovered through three techniques that are possible to find, or three techniques, I shouldn't say all techniques, three techniques that are possible to search for binary stars. One through looking at the light variation, which is shown here, eclipsing binary stars. You can look for them through radial velocity variations, and you can look for them through astrometric variations. And all three techniques are revealing the presence of binary stars. So that's leading to a host of new work today that's looking at whether or not binary stars can explain the host of other unexpected results that have been seen. In other words, can it explain why some of the young stars, in particular the ones that are closest to the black hole, look young? In other words, they may not actually be as young as they look today. A merger would reset the clock. And whether or not there's a dearth of old stars simply because the outer layers of old stars are being stripped off by this interaction. Okay, so lots more to do, both on this front and many, many other fronts. All of this drives further advancements in technology, both in terms of the interferometry as well as the ability to make high-resolution images. Today, central to the ability to make high-resolution images with adaptive optics is the ability to make artificial stars in the atmosphere. So we shine a laser tuned to the transition in the sodium atom. There's a very thin layer of sodium atoms that are trapped up at about 90 kilometers, and you can stimulate those sodium atoms to shine. 90 kilometers is high, but it's not that high. So in fact, one of the problems that one encounters as you go to larger and larger telescopes is you get what's known as the cone effect. In other words, that single laser guide star is not probing the same volume of atmosphere that stars are going through. So it's a cylinder versus a cone. So the solution to this, of course, is to launch multiple lasers. This is like doing a CAT scan on the atmosphere. So there are multiple projects all around the world, and in particular at the VLT and the Keck telescopes that are advancing this multiple laser idea. And this is critical because there are three major projects that are aiming at even larger telescopes. So this is the 30-meter class of ground-based telescope, the European Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope. So all three telescopes depend on our ability to reach this next more advanced form of adaptive optics because the cone effect gets even larger. All of this will allow us to see the center of the galaxy more precisely, which will allow more advanced measurements of physics, but also to see a population of stars that we can't see today. It's really important to know that we are just seeing the tip of the iceberg. Our main source of confusion is just stellar confusion, that you're working against a background of unresolved stars. So let me conclude by saying, if nothing else, I hope I've convinced you that our galaxy is home to a supermassive black hole. Its mass is 4 million times the mass of the sun. And the case for the supermassive black hole there has been advanced by a factor of 10 million over the last 20 years. And that's thanks to this incredible advancement in technology. And today, thanks to this discovery, we have a wonderful laboratory for understanding both the physics and astrophysics of black holes. Thank you for your attention.
Awesome, thank you. Questions?
That was an excellent presentation.
Thank you.
However, the most important fact about black holes has not been answered, and that is what constitutes a black hole. I have two concerns. Number one, astrophysicists don't seem to be working on the definition. And number two, people like myself who have defined what it is. And basically, I've defined 22 matter-force particles, which are the constituents of everything in our universe. I am being ignored. So how do you expect the most important question of what a black hole is to be answered if no one is working on it, and the people who are working on the definition are being ignored?
Well, fortunately, there's more and more attention being paid to black holes every day, and it sounds like you should share. I'd love to chat with you after the session.
But is anyone working on the definition of what is a black hole?
Oh, there are plenty of people working on the definition of what a black hole is. And the hope, I think, of these various tests of the gravitational field is to advance our understanding further. Thanks.
Really nice talk. I wonder if you could say a little bit about observing neutron stars near the galactic center.
So there are a number of experiments that might reveal neutron stars. One of them is the search for pulsars, so magnetized neutron stars. And one of the challenges associated with seeing those pulsars is the screen in front of us, between the center of the galaxy and us, which disperses the radio light. So that's been one of the challenges. Although, I guess it was in 2014, there was the discovery of a magnetar. So a strongly magnetized case was discovered. The other way in which one might be able to infer the presence of the neutron stars is through binary star systems, in which where there's a host star that a donor star that feeds an accretion disk around the neutron star. So there's been this question of whether or not the presence of X-ray sources, so there was a very nice paper written on this about a year ago, is revealing the presence of this neutron star population. So these are questions that are actively being worked on from a variety of different angles.
Just a quick question. Will the next passage of SO2 be visible in the 6 months you can get to see it?
That's a great question. Probably, but of course you have this propagated error of the orbital period and the timing of closest approach. So as you get closer, you have a better understanding of that window. So yes, with a large window.
Okay.
You mentioned there's this assembly of relatively young stars orbiting the galactic center. Could you say again how old they are?
So here I have to be really careful. So there's a population of young stars that we know are young because they're incredibly massive. We think they're roughly 60 times the mass of the sun. And we think those are roughly 4 million years old. Those are the ones actually that are out in that in the disk,
right.
Very clearly. They don't reside in the central region. So in all those little tiny animations, we're looking inside that disk. And inside those that window, you don't see the 60 times the mass of the sun objects. You see things that are roughly more like 10 times the mass of the sun. So they could be 1 million, but they could also be as high as 100 million. And so one of the questions is whether or not that tighter population came from the most recent burst of star formation, or whether or not you're seeing an accumulation of past star formation events, or what interests me the most is the merger products of these binary stars, because their orbital properties are actually quite similar in a sense to these tidally interacting objects.
So thank you for that additional information. I think of the galactic center as really old, and all the dust should have been vacuumed up billions of years ago. Why is there still dust there for new stars to form?
Okay, so and do you mean vacuumed up by the black hole? Is that what you're?
No, vacuumed up by whatever.
By whatever.
They
Okay.
should have just finished by now.
So there is a notion, there is a model for the center of the galaxy that suggests that star formation is cyclical. So outside this stellar disk, there is a clear ring or reservoir, I should say, of gas with a really big hole. So the one picture that was put forward by Mark Morris is the idea that when star formation, the epoch of star formation, in other words, when there's a lot of activity from young stars, and so in fact that's an important concept, that young stars drive a lot of activity or put a lot of energy into the environment. So once those stars have aged and are no longer such a source of energy, then the winds are no longer holding off that gas. And then you get the ability for that gas to inflow and provide the next disk that can form stars. It forms. So the 10 to the 7th years is really set by the lifespan of activity for the really young stars. So that's the working model.
Okay, thank you. That's helpful.